Okay, picture this. You're sitting in a high-stakes technical interview. The interviewer just asked you to find the longest contiguous subarray that meets some specific condition. Your heart rate spikes, panic sets in, and what do? You immediately default to writing out two nested for loops. You confidently hit row and boom, time limit exceeded. The absolutely dreaded TLE error. Look, it is a terrifying moment, but it happens to thousands of candidates every single day because they just naturally fall back on that sluggish O of n squared brute force logic. Well, let's dive into this today and fix that instinct forever. Welcome to The Explainer. Today, I am putting on my ex-Google interviewer and ICPC coach hat. Because listen, this isn't just going to be some dry theoretical lecture. This is a masterclass designed to completely rewire the way your brain works. By the end of this explainer, whenever you see a problem asking for a substring, a subarray, or the longest or shortest contiguous range, your brain is going to automatically trigger your ultimate optimization weapon, the sliding window pattern. I want you to notice the sheer difference in scale here. A brute force approach checks every possible subarray, right? That means you are constantly recalculating the exact same overlapping elements over and over again. Think about it. If you have an array of 1,000,000 elements, you're looking at 1,000,000,000,000 operations. It's sluggish, it's redundant, and it will fail the interview. The sliding window approach, however, gracefully drops that time complexity all the way down to a linear O of n time. Our ultimate goal today is to really understand how we eliminate all that repeated work. So here's our roadmap for this explainer. We're going to start with the core intuition and some real-world analogies. Then we'll break down fixed versus variable windows, tackle the tricky longest versus shortest logic, cover those super common interview traps, and finally, lock in the ultimate pattern recognition matrix. Okay, section 1, intuition and analogies. Let's step away from the code for a second to visualize exactly what this looks like. Imagine you're at a school assembly. You need to find the total height of a group of 10 students standing in a row. So you measure the first 10. Now to find the height of the next group, students 2 through 11, you don't start counting from scratch all over again. That would be crazy. You just subtract the height of the first student who's leaving your group and add the height of the 11th student who just entered. You've effectively just slid your window of 10 students one spot over to the right. It's exactly like dragging a magnifying glass or a text scanner straight across a page. And that brings us to the formal definition. The sliding window is essentially a technique that reuses previous calculations over a contiguous sequence. You are simply maintaining a state. Maybe it's a running sum, maybe it's a frequency map, and you're just updating it as the boundaries of your window move forward. The entire point of this technique is to prevent recalculating overlapping data. Honestly, if you can just remember that you are updating state rather than recalculating it, you've already won half the battle. Moving on to section 2, fixed versus variable windows. Let's break down the two main frameworks. So every sliding window problem in the universe falls into one of these two buckets, and the divide is actually pretty stark. In a fixed size window, the size, let's just call it k, is explicitly handed to you in the problem statement. Your goal is usually to find a maximum, a minimum, or an average within any contiguous block of that exact size k. On the flip side, in a variable size window, the window size is not given to you. In fact, the size is usually the actual answer you are trying to find. You have to dynamically grow and shrink the window to find the optimal size that meets some specific condition. Let's look at the mechanics of the fixed size window first. It is an incredibly reliable 4-step cycle. First, you compute the state for your initial window of size k. That is your baseline. Then you start sliding. Step 2, you add the new element entering on the right. Step 3, you subtract or remove the old element leaving on the left. And step 4, you update your best answer. Add, remove, update. It's this beautiful, mechanical, rhythmic loop that perfectly avoids recomputation. Now the variable size window, that's a bit more dynamic. Here you're working with a right pointer and a left pointer. Step 1, you expand the window by moving that right pointer forward, absorbing new data. Step 2, you evaluate the window against your specific constraint. Basically, is it still valid? Step 3, if the window breaks the rules, you enter a loop to shrink it by moving the left pointer forward until it's valid again. And step 4, you update your optimal answer. Think of it like an inchworm, just expanding and contracting as it moves across your data. All right, section 3, longest versus shortest logic. Now pay attention because we are officially entering the danger zone. This right here is the exact spot where candidates get confused, mix up their logic, and ultimately fail their interviews. Getting this logic backward is the absolute #1 source of bugs. Look at the difference. If the problem asks for the longest valid window, you want to expand eagerly. You shrink only when the window becomes invalid, and you must update your answer outside the shrink loop once the window is safe again. But if the problem asks for the shortest valid window, your logic flips. You expand until the window is valid, and then you aggressively shrink it while it remains valid to see exactly how small you can squeeze it. Because you were checking valid states during that shrink phase, you have to update your answer inside the shrink loop. You absolutely need to memorize this distinction. Now, very often, a simple running sum just isn't enough to track your window state. You're going to need a hash map. Hash maps are essentially the perfect companion for sliding windows, especially for classic string problems, like, say, finding the longest substring without repeating characters. When an element enters the right side of your window, you increment its count in the map. When it falls out the left side, you decrement its count. But here is the real secret sauce. If that count ever drops to 0, you must completely delete the key from the map. That's the only way to maintain an accurate count of distinct elements inside your window. Let's move on to Section 4, Common Traps. Interviewers love to throw in edge cases to test you. Trap number 1, trying to apply a sliding window to a subarray sum problem when the array contains negative numbers. Seriously, do not do this. The entire logic of a sliding window relies on what we call a monotonic property. That means as the window grows, the sum is supposed to grow, and as you shrink the window, the sum is supposed to decrease. But if you have negative numbers in the mix, shrinking the window might actually increase your sum. It breaks the entire window invariant. If you see negative numbers in a sum problem, drop the sliding window immediately and reach for a prefix sum with a hash map instead. Trap number 2 goes right back to what we just talked about on the hash map slide, forgetting to delete 0 count keys. If a character's count drops to 0, but you leave that key sitting there in your map, any logic you have that relies on checking the total number of entries in the map, like seeing how many distinct characters are in your window, is going to be completely corrupted. It is a tiny, silent bug, but it will ruin your algorithm and it will absolutely cost you the interview. And finally, Section 5, the recognition matrix. Let's build out your ultimate mental cheat sheet. Read these triggers on the screen and literally burn them into your memory. Find the longest substring, boom, that's a variable sliding window, longest template. Smallest subarray with sum greater than, variable sliding window, shortest template. Contiguous elements of size k, fixed window. These specific phrases are your golden tickets. They are going to allow you to confidently identify the optimal O-event solution within the first 60 seconds of the interview, while the other candidates are still just sitting there wondering where to even begin. Before we wrap up, I want to leave you with a massive pro-interview tip. Before you write a single line of code on that whiteboard, I want you to look at your interviewer, make eye contact, and say this out loud. My window invariant is, for example, my window invariant is that no character inside the window appears more than once. Doing this does 2 huge things. First, it completely forces you to clarify your own shrink condition. And second, it gives the interviewer a perfectly clear mental model of your algorithm right from the start. It projects massive confidence and seniority. So, here is the final thought I want you to take away from this explainer today. The very next time you're faced with a contiguous subarray or a substring problem, and you're under the intense pressure of a ticking clock, what exactly are you going to do? Are you going to panic and reach for a redundant, slow, nested loop? Or are you going to recognize those triggers, state your invariant out loud, and confidently slide the window to an optimal solution? I think you know exactly what to do. Thanks so much for joining me on The Explainer, and happy coding.